My name is Jim Van Wert. I gave a talk here, I don't know how long ago, but it was on diffusion, thermal diffusion galvanizing.
We liked it.
You liked it, good. This one you're going to like too. I think this is really interesting technology. I'm not practicing the technology, but I did some R&D work for the technology for another company. And you'll see, I'll talk a little bit about it later. But if you're looking for a near net shaped part, this is the process to use. The more complex, the better. If there's a part, I see Joe back there, you're going to like some of these parts. You're going to think about how to do these.
Yeah, I'm looking forward to this.
Because if you're welding parts together or you're having to do a lot of machining, this process takes a lot of those steps out of it. So a little bit more about me, maybe somebody I think introduced me. I've got a doctorate in material science, undergraduate in Aeronautical Engineering, and a bachelor's in Metallurgical Engineering. I've been doing metallurgy for probably 40 plus years. I have a business here at the Mound where we do the thermal diffusion galvanizing. That business is going crazy right now. It's just unbelievable. We just put another oven in to go more capacity, another 30% capacity, and we're now thinking about a second shift. So, it's, all right. So the conventional method for metalworking. You'd start with maybe a piece of metal here off to your left, and you'd go up and you could partially machine it, the gear profile. You can kind of see all the way through this thing where you'd have to go through a bunch of different kinds of machining operations to produce a part like this. With metal injection, think about going directly to that shape. So what you see is in the middle where the powder, and we'll get into it a little bit more, the powder gets injected into a mold. And so that's a green part. Takes a lot of the other secondary operations out of the equation. So MIM stands for metal injection molding. And you'll see more pictures of some of this equipment. So it's a marriage of powder metallurgy, and plastic injection molding. So if you think about plastic injection molding, you're pretty much plasticizing the plastic and you're injecting it under pressure into a die or a mold. Powder metallurgy, they do some things where they compact the powder into a mold. So you say, well, what's the difference between powder metallurgy and metal injection? And I'll get into some of those differences. But some of the keys to that are the complexity you can't get with the powder, the density you can't get with powder metallurgy. And then the advantages of metal injection molding is I can customize the alloy. Some alloys you wouldn't even be able to cast because of the metallurgy side of it. It's not castable, not manufacturable. We made a stainless steel, and we'll get into that, fire protection sprinkler head that had to take a certain amount of corrosion protection, temperature, and all those things. We were able to customize the powder to be able to achieve the kinds of properties we wanted. This technology is used in electronics, automotive, defense, some of the sporting goods. What you'll see, I'll show you a little bit later. Are any of you deer hunters or any kind of hunter? If you're a bow hunter, you know what a broadhead is?
Yep.
Broadhead is kind of the tip of the arrow. Those tips, those broadheads are actually made with this process. Net shape, no machining, no nothing. So here's the MIM process. You compound the powders and a binder. Some of the binders could be wax, and they hold kind of the powders to stick together. Obviously, you're molding it, the binders are melting, and it carries the powder into the mold. And these molds are aluminum molds, So very inexpensive molds. So now you have what they call a green part, and that part is injected. It's taken out of the mold, and I'll show you that in a minute. Then you want to be able to get the binder out of that green preform. It goes into a different kinds of process. It could be thermal, it could be different things, and the binder goes away. So now I've got a part that is powder in the shape of the final part. It then goes into a sintering operation, and I'll explain sintering in a minute. But sintering basically then takes those discrete particles, and I've got a picture of the discrete particles, the bound particles, and the particles that are actually then bonded. So you'll end up with a density, you may start with a density of 70%, all the way to 95 to 100%. It's amazing what you're able to do. So here's the fine powders, 20 micron kind of particle size. And there's thermoplastic wax binders. They're all mixed together, and that's the feedstock that's used to inject into the process. So the feedstock is injected into a metal mold, and that forms kind of the net shape. So you see off to the left is just a conventional kind of molding machine. The tool. So the tools are very similar to plastic injection molding or die casting or squeeze casting. They're vented to get the air out because you've got to dispel the air as you're injecting the powder into the mold. Then you can see kind of the parts, those are the green parts, and then they get sintered. So here's the process, and you can see these are big furnaces. They're under pressure, and they basically remove the binders from the part. Yes, sir.
You say, I don't think you've said primary binders before. Are there multiple stages of debinding?
There can be, yes. You can, depending on the complexity of the part, you may have a two-stage binder to be able to try to control the size of the part.
And they're typically organics? They're not another in the metals column?
No, they're not. They're organics, yes. They're a wax, a thermoplastic, those kinds of things.
My impression was that in plastic injection molding, there are substantial pressures, and the molds for those were high-strength heat-treated steel. What kind of pressures are achieved in the mold? In molding?
This is very low pressure, and the molds are aluminum.
So you said. What are the injection machines? What is the mechanism for extruding or pushing the mix?
It's basically starts with a shot sleeve, so it's a cylinder. It has a piston, so it injects the powder into the cylinder.
Okay.
The piston does it's basically two stages. The first stage is it kind of pushes the powder up against the mold, and then the second phase is where you actually push it in, and then the third phase is an intensification phase.
Thank you.
I understood I don't practice the process, but I studied it pretty well, and so the parts are slowly heated to protect, in a protective atmosphere, so you don't oxidize some of the metal particles. And that drives out the binders. Once the binders are evaporated, again, that's the green part, and then it goes into the sintering oven, and that's really where those particles will actually form together.
You mentioned in your first slide, you said you might add alloying elements in there as well. Is it during sintering that you might have diffusion making alloyed components that were not there to start with?
Yes, in some cases, yes.
Okay.
So here's an example. The binder, the feedstocks, different metal alloy. There's your green part in the middle. And then one of the keys that really is, see this sintering shrinkage? This is the challenging part of this process, okay? It's the shrinkage. During that sintering, think about particles being pushed together, forming together. So you have to really, in today's world, they're much better because they can use computer simulation to kind of predict shrinkage, because you have to think about the shrinkage in 3 dimensions, not just, it's linear and I'm going to shrink this much. No, it's going to happen in all three 3 and
You mentioned that this sintering, that's purely a thermal process, it's not a isostatic pressing or anything?
It is it's under pressure, okay? Not isostatic pressure. I mean, that's very high pressure. This is moderate pressure under an atmosphere to keep things from oxidizing.
So Jim, for stainless, what would be the sintering temperature?
I don't remember, to be honest with you. I can get it for you.
I was just wondering typical temperatures.
It's sintering, you know, the sintering temperatures are enough to where you're actually getting the particle to soften to some degree and come together. So
But it does not melt.
it does not melt, no.
Okay.
There's no molten state.
Gotcha.
Yes, sir.
Jim, how do you get the feedstock or the metal powder to fluidize into the molds in a non?
That's the tricky part, okay? It's in what they call a shop sleeve, and they'll air and train that so it's fluidized, and then they use the piston to push it, and then your mold has got a lot of venting in it to be able to vent the air as you're injecting and fluidizing to inject the air out of the mold. So that's their secret technology.
What's the thermodynamic aspect, or what's the driving force that causes this stuff under moderate pressure? It's not being mechanically driven together. What causes it to shrink, to come together to the density?
I'm going to show you, you guys hold on to that question. I'm going to show you something and you'll kind of see it right here, okay? So think about phase 1 and you can see discrete particles, right? And you can see the gaps between those particles. The phase 2, when I got rid of some of the binders, they started agglomerating and coming together. So that's part of your shrinkage when you get rid of your binders. And then you can actually see in here, Joe, this is the answer to your question, these are actually now bonded together. They're not melted per se, but the particles are actually pushed together under that temperature and pressure, and they bond together. So you'll have potentially a void here. So why MEM? We'll go through some of that, but you can kind of see off to the left is you can see they're very small injection machines, not very big. The center one is the debinding, and you can see those are pretty substantial. I mean, you can see the size of those doors.
Twice you've said that look how big these are. Is it because intrinsically they need to be, or no, we want to do a bunch of them? We need a large load of
The
parts.
answer is the second half. This is designed for, you can do small volumes, but it's designed for high volume. Okay, that's where you'll see some of the types of parts, but that's where the inherent benefits are. You can see these are all parts that are in a rack, so they're well supported, and they go into this sintering oven. Some cases, if they're not, they will sag, and you'll get distortion, so you have to kind of put them into a fixture, support them, and then when they go inside the oven. So this versus others, this was a kind of a neat, so production quantities, and so this will answer your question, why are we talking these large ovens and things? So if you talk just press and sinter, which would be powder metallurgy, machining is down here, so the lower complexity, lower volumes. Investment casting is kind of the medium to high volume, can be. And then you look at production quantities. This is the sweet spot for metal injection. So the more complex the part, and the more parts you can make, obviously you can really reduce the cost. So here's cost. And this is probably everybody's asking this question. So again, complexity, horizontal axis, you can see the more complex and the lowest cost per unit, that's where MEM is.
What, between a regular machine part and this MEM part, how would the tensile strength of the two parts, if you can make the same part in either fashion, what would the tensile strength be? How would it vary?
I'm going to show you, I got a graph for that.
Good, okay.
So, good question. And it really depends on what do you do to the alloy, okay? I can cheat a little bit by formulating the powders to give me some more strength, but intrinsically you'd say, powder metal's going to have, or MIM's going to have voids. It's not going to be 100% dense. The metal parts, typically rod alloys or bar stock and things like that, are pretty dense, okay? So you'd say, the machine part's going to be higher strength.
That's what I would think.
That's what you'd think. But in some cases, we'll show you it's contrary to that. So.
Does it depend on the powder size also, Jim?
It does. You can use multiple powders. If you saw that, I'll back up real quick. You see how you saw that little particle? What you can do is you can blend different size particles, which will fill the lattices and the voids, and you get a better density of the part, or of the part. So you asked about tensile. You must have saw my slides already. So this is a comparison of powder metallurgy versus MIM, and you can see it's substantially different. The reason there is the density. Okay, powder metallurgy is maybe 70 to 80% at best dense, where this case we're in the 90s. But it didn't answer your rod alloy one. So here's kind of, if you looked at density versus tensile strength, elongation, hardness, complexity, surface finish, production volumes, kind of those things in cost, you can kind of see where MIM is versus, let's say, for example, in machining. Machining is high cost, the range of materials is good, production volumes, yes, you could do a lot of them, but you'd end up with lots of capital and those kinds of things with lots of machines. Investment casting, the lead time on investment casting, because I do a lot of investment casting consulting, the problem is the lead times, because of the process steps, can be very long and be a challenge. Complexity, you can't quite get there. Then you have the other side with investment casting. You're using molten metal, Joe, and you have to, how do I flow it? How do I solidify it? How do I cool it? How do I do all the kinds of things that I have to do with a casting? So here are some of the alloys. So in the stainless steel, Joe, you can see, 17.4 pHs, 304s, 420s, some of the high 440Cs. 440C, we actually built a die insert for rubber injection molding, and it was an insert that we used a lot of, and we made it out of 440C because of the wear characteristics, because of that. 310s, the corrosion resistance, the 316s, the 310s with niobium, lots of steels, Inconels, wasp alloys. So it's they're and then you get some of these other MIM alloys where they've actually developed their own alloy used for MIM the MIM process. So here's some complexity. So if you needed a part with a lot of angled holes, who cares? As long as you can draw it out of the mold, it works. There, all the way to the left, that's a broadhead that I talked about, the arrow. Think about that, trying to machine one of those and what it would cost. Or even trying to cast it. Those thin blades are less than 40 thousandths.
Typically in plastic injection molding, you have injectors that go in to allow to make holes and things like that.
Yeah, the pulls that would go opposite directions.
You do the same thing here.
Yes, you would. Threads, casting the threads, all different kinds of other knurlings, any complicated profile. And tiny parts are just probably better than even the bigger ones. You have a certain size where you can go to because of the shrinkage. So you can kind of see the Da Vinci robot. A lot of those parts on the Da Vinci robot are metal injection molded, out of stainless. Power tools, some of the housings on the power tools, some of the complexity inside the gears. Sanitary, there is a company that's actually making a lot of the faucets and making components using that. Aircraft, computer hardware, electronic connectors, some things in automotive, and I'll show you mobile phones. So here's some case studies. So here's basically a slack adjuster, and it basically adjusts in a brake system. You can see the part down here. So here's the problem characteristics, the solution, and the results. So that they saved 40% in a cost reduction. Who wouldn't give 40% cost reduction in a lot of these kinds of components? It's a big deal, especially automotive when they only want you to make 5% margins. Here's another one. Somebody talked about nozzles. I think you did. Here's a fuel injection nozzle. If you tried to go back and try to machine all the tiny ports for fuel injection, it's very expensive. That's why changing out injectors I just did it in my truck, just to do the injectors was $4,000. It's ridiculous. Perfect part though. Those holes that are in there are 0.5 millimeters in diameter. 0.5. This is one of my favorite ones. So this is started out as a stamping with bar stock pins, riveting the pins in, then plating it. As sintered and plated, everything's all in one. So you think about all the labor savings, machine setups, and all those kinds of things. Big deal. This is the one I was talking about. So if you look at these fire protection, the picture on the left is called the deflector. And what the deflector does is, that's what disperses the water. And so, it depends on the room, how far do I want the water to be thrown. You know, if you look at the layout on here, it's every 10 feet or so, because that's the spray pattern. It has to be pretty tough. And then you look at the frame. And when we started, this was the early prototype. I really said, you think you can really do it? So we made a very simple die, aluminum die, and we made it. And so I'm just going to show you. So you can see this is the wrench boss to install it. There's where the threads go. And in the center of that is what they call the pit cap. And what the pit cap does is it sits in that seat. The glass bulb, and these are not glass bulbs, but a lot of the sprinklers have a glass bulb in, and they're rated at a certain temperature when they go off for fire protection. So a lot of them are 158 degrees. Once they see it, the bulb breaks. There's a spring, a wave spring underneath that little deflector, or that seat that sits in there, pops out of the way, and you start flowing water. So the top up there, there's a torque screw that goes in, and you actually apply a specific torque to the bulb that pushes down on the pit cap seat. Those are very precise. At Victaulic, we developed a way to put these together automatically. So in an automated cell, we replaced 14 people, or displaced 14 people by automating the entire process. But as I said earlier, one of the keys here was to make a stainless steel sprinkler was a big deal. And if we could, the lower cost we could make it, they knew they could sell them for a lot more money. So as I said, we were paying $1.70 for the frame machined and everything, and selling it for $20 to $25. So everybody would like those kinds of margins. And so this is one of the Victaulic hot selling for specific applications, sprinklers.
How, your sprinkler retail, what would it sell for versus the traditional sprinkler that was made by a subtractive machine? What would that
Oh,
compare?
to make stainless steel,
Yeah,
the stainless steel one was about $14 to machine.
just to, but to buy the whole thing, what would it sell for?
Well, they're gonna sell in the $25 range. That's the selling price.
So you were less expensive.
We were
Profit margin.
$1.70 versus $25 selling price. That's why I said, everybody would love those kinds of margins. So they love selling stainless steel sprinklers. And they're one of the largest in the world in selling fire protection systems. I'm coating all kinds of, in fact, we just won the contract for, it's called the 009V, which is the couplings for fire protection, from 1 1/4" all the way to 12-inch diameter couplings. And we're going to coat all of them and to be used in the galvanized kind of area, or the high corrosive areas. So here are some other parts that near and dear to my heart, because I'm a gun fanatic, but a lot of these gun parts are made with men. Ruger and Smith & Wesson were the early adopters of using this technology in making. That's why you see some of their gun prices are more competitive than other people, because they'll machine them out of forged parts and what have you. So you can see just a myriad of complex parts. All right, so we're gonna, we're gonna give this a go. So the guys that I worked with at Indomem in India, they had this YouTube video, and it's pretty amazing. It'll walk through, it'll show you kind of some of the same things, but I figured it's better to see a nice video at the end of this, so. Uh-oh. We're getting the YouTube commercial.
Yeah.
So you saw it come up, the parts were captured and captured.
We see that again?
That's what I was gonna try to do, I don't know how to do it. Hang on, a
So
second.
quick.
Hang on, that's all right. We have the technology here.
Push the little
See it? Did you see it come up? Those are the parts in there. So there it is, coming out of the machine, setting them there. They'll get placed in carriers. This is the desintering, or I should say debinding. They have 1 million square feet under roof. So it's a little place.
On your last slide down at the bottom, it said Indomem Confidential. What was there about what we saw that was confidential?
Just happened to be in some of their slides.
Okay.
They gave me permission to use it, so.
Um,
And it's on YouTube, so anybody can look at it.
Well, no, I meant the previous material, perhaps it was. You have a straw man that you've compared to several times, conventional
Powdered metallurgy.
powdered metal.
Mhm.
Can you give a quick rehash of how does powdered metal compare to what
Okay.
you just described to us?
Basically, powder metal is, you put powder into a die, in an open face die, and you close the die and you basically are compressing it.
All right, so it doesn't have the fluidization aspects, it doesn't have, it has one axis of compression. They could use perhaps the same competence and skill at getting the right metal mix if they wanted to.
They do,
But it's primarily these aspects of the mechanical handling
It's,
of it.
it's the complexity. Yes, all your things that you just described, but the biggest one is complexity. You can't get the complexity. Yes, sir.
So, would MIM be appropriate for casting like artificial joints like knees and hips?
Yes,
And do they use the
Yes.
MIMs for that?
yes. Certain applications, yes.
Like titanium?
They can do titanium, sure. You know, that's the advantage here, is what alloy do you want? You know?
Is that a limiting consideration, or is it, no, we can pretty much make powders of most of the useful metals, as we've learned how to do that?
Oh, yeah, absolutely.
Okay.
Yes, sir.
You had mentioned a lot of the molds are made of aluminum. Is
Yes.
that true in all cases? I was kind of surprised to hear that.
Well,
You said
there's-
it's low pressure, low temperature, but I mean, I'm just surprised. to hear
In
that.
some of the areas where you might have some erosion, and I'm sure you're alluding to, you know, if you inject metal or powders in something, you get abrasion, and they'll use inserts to take care of the wear. Maybe they'll use a tool steel in a particular area where you're injecting, but most of them are aluminum.
How do you get the powdered metal? How do you make that 20 micrometer?
So it's
How
in
do
a-
you take-
It's
you
in
know,
a mixer, and they'll have a mixer with
Well, I mean, you got-
blades in it.
You've got metal that you heat that's a liquid or a solid. How do you turn that into those particles? I mean,
Oh, you buy-
if you grind it or something
No, they
like
buy,
that,
you
you
buy,
get abrasive.
other people make the powder,
How do they do that?
and, well, I can only speak for aluminum powders, because when I worked for ALCOA, we did a lot of that. A lot of that is dropped through a screen, so it's molten, and it drops through the screen and makes a part. Yes, similar.
Jim, it's probably the same particles they're used for 3D printing, right?
It's very similar, and in fact, another technology that I'll talk to you and Doug about is, it's 3D jet printing. And it's the next, we're gonna see a talk about metal and 3D printing in, I think, September, right, Doug? Yep. One of my colleagues that works with me, he went to work for a company that developed technology to do 3D metal printing. And if you're familiar with 3D printing, you know, you end up with a whole bunch of lattice structure that you have to trim away and clean up, and it's a lot of work. The technology that they did doesn't have any of that. They're using lasers to be able to do a lot of this. And but there is another technology called 3D jet printing. That's same thing, Joe. It's powder bed, and it's sweeping the powder and curing that layer. Question? Yes, sir.
Could you talk a little more about why this process is better than 3D printing for certain parts?
All the extra work that you have to do to clean up a part, a 3D metal printed part, or even a 3D plastic part, there's a lot of people think, oh, it just comes right out there and it looks like this. If you've ever seen them, they're very rough, a lot of work. There's a lot of cleaning and a lot of work to do to get to the final part. So there's a lot of labor, where in this case, you sinter and it's done. Okay, it's ready to ship. There's no labor. So it's really complexity and labor savings. Yes, sir.
The top of your chart that showed materials that were at least known and workable, available at present, I think you had a category of case hardening alloys. Are those made in a form that can then be case hardened, or no, if through a tweak of the process, they'll come out already case
They
hardened?
have to be case
What were
hardened.
you showing?
Yeah, they have to be case hardened.
Okay. It's an
They're
alloy.
case hardenable. They're an alloy that you can
That's
case
all I was
harden.
asking.
Yeah.
Thank you.
Yes, sir.
If you have a threaded hole in a part, you know, when you talk about this 20% shrinkage, Is that predictable where you can oversize the part and allow for that shrinkage and have something that has a proper thread
It
clearance?
used to be trial and error, okay?
Better.
But now, with the, the computer power and the simulation characteristics, you can simulate that shrinkage in three directions and three orientations.
Can you come out with a part that you can actually?
Yes. Yes.
Screw bolt into?
Oh.
Maybe not the first one, you may have to tweak it, but that's the advantage of the dies. They're not that expensive, and so if you have to tweak and if you have something like that, what I've seen is they use an insert. So, okay, I got it, now I can replace the insert, so the rest of the holder and the main cavity is okay, and now I can just fine tune that insert. Yes, sir.
So then is the shrinkage dependent on the particle size of the powder that goes in?
Yes.
Is that how you determine that?
Well, that's one of the characteristics. The size of the part is another, and then how do you support it when you're sintering it and debinding it?
So the quality of the particle size of the powder is directly related to the predictability of the size coming out.
Yes, absolutely. And so you'll see in a lot of the plants, it's not any different than the thermal diffusion. We characterize the size of the powder particle because that's what we want to do during our process as well, is be able to predict what's going to happen in the process. Yes, sir.
What type of surface finishes do you typically see?
You'll probably see a 125 surface finish.
Okay, so in some cases you may have to polish.
You may have to, depending on what the application is. A lot of the medical parts
Yeah.
are typically polished. But, I've watched them play around with powder particle size. And again, to the sub-gentleman's point, go to a finer particle, you get better surface finish. It's just more complex when you start getting finer powders. But most of these powders are 20 microns, so they're pretty small to begin with. Yes, sir.
How do you get that binder out? It's at a deeper level in the metal. How does it diffuse? Is it a gas? How does it diffuse?
Comes out as a gas.
It comes out as a gas. Okay, so actually the gas is through
Yep.
the structure of the.
And it's because that structure is got porosity, I'm going to call it porosity.
Yeah.
It comes out of that lattice. And there's where they're pulling a vacuum in some cases to help draw those gases out of the part. What else? Anything else? Yes, sir.
How do these property-wise compare fatigue properties and impact properties?
Impact property is very good. Fatigue, anytime you have not 100% dense, you may not have the same fatigue. Fatigue in a lot of cases is measured by fracture toughness. And I did a lot of studying on aluminum and fracture toughness. And it really has to do with the alloy. So you can influence it by alloy. You can influence it by density, geometry. But from a corrosion standpoint, you get very good properties from corrosion. The impact properties are very good. Yes, sir.
What kind of tolerances can you hold on the part?
Plus or minus 3,000s.
What would you say the largest part that you could make this way?
You saw the,
Are these mostly smaller parts?
these are smaller parts, probably a part maybe 8 or 10 inches long, a few inches wide. You saw the handgun frame? That's one of the larger parts. And, they keep getting, the guys there are evolving the technology and getting bigger and bigger parts. It's all about that shrinkage factor that's driving it. And so the better at predicting the shrinkage, the easier, because it's not any difficult to inject the part. It's a matter of predicting what that part geometry is going to be after injection. Well, thanks very much. Appreciate it.